Good afternoon, folks. Can you hear me?
Yes, sir.
Okay. You all can see the blackboard?
Yes, sir.
Right. So last week we were looking at
Recording in progress.
right. So last week we were looking at Euler's torsion function, right? And that is denoted by psi n, right? Where psi n defined as the number of positive integers less than n, right, that are relatively prime to n. And what does relatively prime mean? Anybody? What does relatively prime mean? If one number is relatively prime to another, what does it mean by relatively prime? What is this here? What does this mean? Anybody? Relatively prime? Here, Rahim Sobas, what does relatively prime mean?
The highest common factor between the two numbers is 1.
Right. Well, the only factor that they have commonly, or the only factor that they share is 1, right? So um, we went on to find what it was, psi 35. Did we find that last week? Was it psi 35? Let me see. 2025. No, it's not this. I'm trying to find the board, but apparently hold on a bit. All right, it's not that one. Today is what? Today is the third. Last week was the
Last week Monday was the 27th.
okay. Right. Yeah, apparently I can't find that. So, uh, let me go back to my whiteboard home. Right, so you all are seeing the same blackboard that we started with, right? You all are seeing that now?
Yes, sir.
Right. So if we do, okay. So I want you all to find for me. I can't remember if we did side 37 or side 35 last week, but I want you all to find side 35, right? So n is replaced by 35, and tell me what you get. So as soon as you get a number, as soon as you get an answer, tell me, right? Okay, anybody get that? You should get it by now. It's very simple. What did we get for psi 35? Okay, what did we get for psi 35? Sherry Sami, what did you get for psi 35? Okay, Dan Kasim, what did you get for psi 35? All right, we want the class to go forward. Somebody answer. Miguel Pascal, what did you get for psi 35? Okay, Micah, what did you get for psi 35?
I feel like I do something wrong here, but I got 0.57, but I don't know if that's correct.
0.57.
Yeah, but
No, watch, remember psi 35, right? Psi n, look have it here, psi n, right? Psi n is defined as the number of positive integers less than n. So psi 35 will be the number of positive integers. So nothing minus. So a negative integer is like -1, -2, -3, and so on. So it is the amount of positive integers less than 35 that are relatively prime to 35. So the integers less than 35 that are relatively prime. And relatively prime means that the only common factor they share is 1, right? So, for instance, factors of 35 are what? 1, 5,
7.
7, and 35. Good? So, if
3.
I want 34 is relatively prime, the factors of 34 is 1, 2, 17, and 34. So the only common factor they share is 1, right? So if the only common factor they share is 1, then 34 is relatively prime. So 34 is a candidate. If I go to 33, factors of 33 is 1, 3, 11, and 33. Again, you notice the only common factor it share with 35, right? These are the factors of 35. The only common factor it shares 1, so 33. If I go to 32, right? The factors of 32 are what? 1, 2, 4, 8, 16, and 32. Good? So, again, 1 is the only common factor because for 35 is 1, 5, 7, and 35, right? So 32 is relatively prime because 1 is the only factor shared. So we have 32. What about 31? Anybody? What about 31? Is 31 relatively prime to 35? Why I didn't write it out is because the factors of 31 are very easy. And you should know, you should be able to work that in your head. So, people, 31. Is 31 relatively prime to 35? What are the factors of 31?
Yes, sir.
Right. 31, the factors of 31 are just 1 and 31, right? 1 and 31. So, compared to 35, 1 is the only factor that they share. Right? 1 is the only common factor. And when 1 is the only common factor that they share, two numbers share, they say it is, they are relatively prime or co-prime to each other. Now, if we go to 30, factors of 30 are equal to what? 1, 2, 3, 5, 6, 10, 15, and 30. Now, it shares both 1 and 5. So it is not relatively prime. For it to be relatively prime, it should only share the factor 1. Right? So 30 is not relatively prime. Good? So, okay, so I want you all to continue working it. So you go and check 29, then check 28, and so on. I want you to go through it because you'll get some practice. And then we'll see how we could make it easier. So go through it and tell me what answer you all get. Now, as soon as somebody get an answer, you could tell me. So we wouldn't have, let me pause the recording so we wouldn't have much space in the recording.
Recording stopped.
So it's if I work out 29, I could see the answer now? Or
No,
this the whole thing?
no. Well, you have the answer already?
Not for the whole thing. I'm like halfway
No.
there.
Yeah, I want the answer for the whole thing. You have to go and
Okay.
check all the numbers less than 35 that are relatively prime to 35.
All right,
Right?
no problem, sir.
Sir, I got 11.
What's that? You got 11?
Yeah.
All right, well, we'll see just now. All right, continue working. So I know 29 will come here. 28 is what? 1, 2, 7. So it can't be 28. 27 is 1, 3, 9, 127. So 27. 26 is 1, 2, 13, and 26. So 26 will be relatively prime. 25 will be 1, 5. So they will share two numbers, 1 and 5. 1, 2, 3, 4, 5, 6, 7. 24 will be 1, 2, 4, 6, 8, 12. 24. 1, 2, 4, 6, 8. All right, so 24 will go here. 23 is 1 by 23. So 23 will go here. 22 is 1, 2, 11 by 22. So 22 will go here. We see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 22, 21 is 1, 3, 7. So 1 and 7, 21 have 1 and 7. So that wouldn't work. 20. 20 is 1, 2, 4, 5, 10. So it have 1 and 5 and 20. So that wouldn't work. It's supposed to be 1 alone. It's supposed to share. 19. So 19 is like 1 by 19. So 19 will go here. 18 is 2, 3, 6, 9. 1, 2, 3, 6, 9, and 18. So 18 will go here. How much I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'll go down to 18 and I get 12. So you all continue, and we know that 17 will also be 1 because 17 is 1 by 17. So the only common factor it will share with 35 will be 1. So 17 will be co-prime also.
Excuse me, sir.
Uh-huh.
I get 16 and 13 for after 17.
Yeah, but you have to go right down to all the numbers that are less than 35. Look at here.
So
So you
I
want the
got
rest of them?
It is defined as psi is defined as the number of positive integers less than n. So all the number of positive integers less than, let's now let me get back the less than 35 that are relatively prime to 35. So you have to go down to 1, straight down to 1. You have to check. Good?
so I got 20 total. For the
20.
Yeah.
Okay. Anybody else get any other answer?
Well,
27 positive integers.
So I got 23.
I get 24.
I get
Oh.
24.
All right. So a couple people get 24. So 24, 24.
Oh wait, yeah. I did my math wrong. Sorry. I had 24.
24. All right. Now it is said that if n can be expressed, right, as the product of two prime numbers, right? Could 35 be expressed as the product of two prime numbers, P and Q? We just call them P and Q.
Sorry, repeat that.
Could 35 be
Yes.
expressed as a product of two prime numbers? Yeah, I hear
Yes.
somebody else saying
7
something.
and 5.
Right, so we'll call it 7 and 5. So we'll say P is equal to, let us say P is equal to 5 and Q is equal to 7, right? So if we could express it as the product of two prime numbers, then psi n, right? Which we did here, then psi n is equal to P minus 1 into Q minus 1. And here we'll get what? 5 minus 1 into 7 minus 1, which is 4 multiplied by 5 minus 1 is 4, 7 minus 1 is 6, 4 by 6 is 24. So yeah, the people who are 24, good. So if we are finding psi n, and n could be expressed as a product of two prime numbers P and Q, then psi n is easy to find. So if I say to find psi 55, oh, just now, I'll have to repeat that. Let me repeat that
Recording in progress.
for it to be in the recording. So if we're trying to find psi, right? Psi 35, right? We're trying to find psi 35. So n is 35. So it is said that if 35 or n could be expressed as a product of two prime numbers, which you all did, this is it here. I should use a different color to go around it, right? If it could be expressed as a product of two prime numbers, which you all give me here, 35 could be expressed as 7 by 5, right? 35, that is 7 by 5, two prime numbers. If it could be expressed as two prime numbers, then psi n, two prime numbers, which we will call like P and Q, then psi n up here, psi n is equal to P minus 1 into Q minus 1. So 5 minus 1, we get 4. 7 minus 1, we get 6. And 6 multiplied by 4, we get 24. Good? So psi 35 is equal to 24. Right? So,
So you have to include 1 as well. You have to include 1 as well.
Yes, to get to 24, because 1, that is when you are working it out manually. Okay? Like how I had you all working it out before.
Yeah.
Because the only factor of 1 is 1, right?
Right.
35 have the factor 1 in it. So 1 will share 1 alone as its common factor with 35. So yes. Good. So 1 will be one of the answers. So okay. Let us find psi 55. You're supposed to be able to work that in your head.
40.
40. All right. So psi 55 is equal to, so what we have to do, remember what it is we're looking for now? If it could be expressed as a product of two primes, right? And two prime numbers will be 5 and 11. So we say let P, let P equal to 5 and Q equal to 11, right? So psi 55 is equal to P minus 1 into Q minus 1, which is equal to 5 minus 1 into 11 minus 1, which is equal to 4 by 10, which is equal to 40, right? So most times in problems, when you get in problems, you'll get n being a number that could be factorized into two primes, okay?
Yes, sir.
So okay, so Euler's Right. So Euler's theorem states that for every a and n that are relatively prime, a to the psi n is congruent to 1 mod n. Okay. Let us just consider um let us consider an a and an n. Okay. Okay, so I should go further and say where psi n is the quotient Okay, so you all could just read that and let that sink in a little bit. So there's a problem in Euler's theorem that I want to give you all, but I'll give you all it to consider during the week. Okay? So I want to move on to the Diffie-Hellman key exchange, which is what? Symmetric key exchange, right? What do we remember about a symmetric key? Anybody? Remember you had symmetric and asymmetric, or you had private and public key exchange. So what do we remember about symmetric key exchange?
With the symmetric key, it's that two people or more would have the same key, which could be used to decrypt or encrypt a message. So if one was encrypted with the key, it's only that key could be able to decrypt it.
All right then, good. So, so the notes for this that we are going to do, I will put it in the sharing is closed. So I will have to put it in the folder. But we'll see about that later. Let me just get a new share. So um,
Recording stopped.
okay, just give me a minute. Let me get the notes for the Diffie-Hellman key exchange. Let me see the easiest way to get it. Okay, folks, in the meantime, I want you all to do this problem for me. So, let's write it down. What is the remainder when 2 to the power of 1,000, and we'll be using Fermat's theorem for that. What is the remainder when 2 to the power of 1,000 is divided by 13? So we want to find 2 to the power of 1,000 mod 13. Good?
So I don't know if you're supposed to be sharing the whiteboard or not, but we're
No,
seeing
no, no.
Canvas right now.
Yeah, that's why I told you all to write it down. I'm not using the whiteboard for it. Right? So 2 to the power of 1,000 mod 13. Right, okay, folks. So the question was, what? Can you all hear me? Are you all seeing the blackboard?
Yes,
Yes.
sir.
What is the remainder when 2 to the power of 1,000 is divided by 13? So what answer did you all come up with? What answer did you all come up with to that?
Still working on it.
You could use Fermat's theorem and see what you get. All right, okay, folks. Um, let's leave that. You all will do that during the week, and we'll consider it next week, okay? Since nobody has gotten it out. So,
So,
uh-huh.
is the answer? Well, I think my left side is wrong. I think I did the wrong calculation. But is it
Okay.
2 to the power 4 mod 13?
No, I wouldn't give you all the answer. I will leave you all to put out during the week. Okay? Right?
Excuse me, sir.
Okay, so
Uh-huh.
No, I just want to know if it was 3, if the remainder was 3.
No, I wouldn't give the answer. I
All
want you
right.
to work it out. And next week we will look at it, okay? Right. So when we do this here, what we are going to do, we will see why we do modular arithmetic, okay? It will show us why we do modular arithmetic. So all right, so here we're going to look at, let me see if it's the recording on. We are going to look at,
Recording in progress.
and it's simple, it's very simple, right? The Diffie-Hellman key exchange, right? It has been built upon, but it's still used. It has been built upon. So they say this is the first published public key algorithm, right? So it's a public key algorithm. The number of commercial products employ this key exchange, and the purpose is to enable two users to securely exchange a key that can then be used for subsequent symmetric encryption of messages. So the algorithm itself is limited to the exchange of secret values, and the effectiveness depends on the difficulty of the computing algorithm. So let's take a look at this for a little while. You all have seen your screen, right? So you can read the left and the right and see what is going on. Then I will explain. Right. So what it says that we have Alice and Bob, right? So they share a prime Q and A, right? A prime number Q and alpha, such that alpha is less than Q. So let us say Alice and Bob share a prime Q and alpha, right? So they share these primes. And alpha is less than Q, and alpha is a primitive root of Q. So what is a primitive root? So let us say that, let us find if something is a primitive root of something. So let us see. Let me see how could we do this. So, right, so I have the blackboard here, right? So let us say find or show, let's see how we will do it, primitive root, right? So alpha and Q. So let us say those two primes are like 5 and let us say 3. So therefore Q will be this, and let us take alpha, which is less than Q, to be 3. So let us show that 3 is a primitive root of 5. How do we show that, right? So first of all, we make a column, we call it N, right? And N will start from 1 to 1 less than 5, okay? So N will be 1, 2, 3, and 4. Good? And then we'll have another column, we'll call it, since we find in if alpha 3 is the primitive root, this will be 3 to the n, and here will be 3 to the n mod 5. Good? Oops.
One second, sir. Can you just repeat that one more time, please?
Yes, what you want to find out?
Can you just repeat what you said just now, please?
Oh, you want at your station?
Oh no, I was trying to take down notes.
All right. So we want to prove that 3 is a primitive root of 5. Why I'm doing this is because in the notes here, in the PowerPoint notes, if we go to the PowerPoint notes here, we will see that up here, Alice and Bob share a prime Q and A, such Q and alpha, such that alpha is less than Q, and alpha is a primitive root of Q, right? So I'm just explaining what is a primitive root. How do we know that one number is a primitive root of another, right? So I took two numbers, Q equal to 5 and alpha equal to 3. And they say alpha is a primitive root of Q. So let us find out. So this is the way that we find out if one number is a primitive root of the other. So the number Q, we'll take all the numbers less than Q, which is 1, 2, 3, and 4, right? We put that in a column called N. And then now alpha is 3. Good? So we'll have a column called 3 to the n. And then the next column will be alpha to the n mod q, which is 3 to the n mod 5. Good? So what will we get under the column 3 to the n? So you also be able to work that basically in your head. So 3 to the n, if n is equal to 1, 3 to the n is what?
3.
3.
3. If n is equal to 2, 3 to the n is
9.
9. If n is equal to 3, 3 to the n is
18. No.
so 3 to the n will be
27.
3 by 3 by 3.
27.
When, right? 3 3s are 9, 3s are 27. And when n is equal to 4, 3 to the power of n will be 3 to the power of 4, which will be 3 multiplied by itself 4 times, right? And we will get what?
81.
81, right. So now we go to this column, 3 to the n mod 5. So now it will be 3 mod 5 will be equal to what? 3 mod 5.
That would be a 0 remainder 3.
Right, 3. Right, so the remainder is 3.
That's
So modular arithmetic, we're looking for the remainder, right? So when 3 is right, so it's A is equal to Qn plus R, right? Good.
Yes, sir.
So 3, which is A, is equal to 0 times 5 plus 3, right? Where the quotient is 0, right? And n is 5. Remember we did that? A is equal to Qn plus R. All right. What is 9? So 3 to the n now is 9. So 9 mod 5 is equal to,
4.
right? And 27 mod 5 is equal to,
2.
right? And 81 mod 5 is equal to 1, right?
1.
5/16 are 80, remainder 1. So we notice that we have in this column here the same thing as we have in this column here, right? The same set of numbers, right? 1, 2, 3, and 4. Good? You all see that?
Oh,
It's not in the same
yes.
order, it's not in the same order, but we get the same numbers. Good?
Yes.
The same elements on the n are the same elements that are on the 3 to the n mod 5. So if we have that, then we know that 3 is a primitive root of 5. Good?
Yes, and you wouldn't have to do like a bunch of numbers. You just have to have a couple to confirm it.
You wouldn't have to do what?
You would not have to do a whole bunch of numbers, but just have a few to confirm it. Yes.
No. If I want to find out if 3 is a primitive root of 11. So here we found out 3 is a primitive root of 5. Good? We have to work out and see if when you work out everything, because 5, we have to take all the numbers less than 5 and put it in the first column, right? We call that column n. The numbers less than 5 will be 1, 2, 3, 4, 5, right? So if I had 11 here, if I want to find out if 3 is a primitive root of 11, if instead of 5 I had 11, what will I put in my first column here? What are the numbers I'll put in my first
1
column
to
here?
10.
Right, 1 to 10. Good? Right?
Yes.
In fact, let us find out that then. Let us find out if 3 is a primitive root of 11. Good? So,
Yes.
so let me clear the canvas here and let us just do that as a practice. Show that 3 is a primitive. So you all work it out. Primitive root of 11. So what you have to have here is n, right? 3 to the n, right? And then 3 to the n mod 11. Good?
Yes.
So here we have this. Then we'll have a row for 1, 2, 3. Right. So what you could do, go online and just bring up a modular calculator, right? And that would help you.
So you can repeat that?
I say you could go online and bring up a modular calculator from online. Online, just type in modular calculator. So on the end we'll have just now, what? You'll see what I'll do. On the end we will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So on the 3 to the end, right? When you reach like 3 to the 5 and 3 to the 6 and so on, you could use your calculator for that and find the values here, right? Use your calculator and find the values here in 3 to the end. And for 3 to the end mod 11, you could go online and type in online modular calculator, right? Or online modulo calculator, and you'll get one and you can work out the column. Because like on your calculator, you'll work out 3 to the 11, that will give it quickly, right? Your calculator will give it quickly. Let me see. Um, Three to the 11. X to the Y 11. Right? Yes, on my phone I even get it. For 3 to the 11, they give me, sorry, we wouldn't have to use 11, right? It's all the whole numbers less than 11. On my phone, I got 3 to the 11. So you could use your phone to get the 3 to the n column and then go online, just type in modular calculator, right? And you'll just have to type in the number, 2 numbers, right? So like, for instance, if I was using like 3 to the 11, it gives me as what? 177, 147 mod 11. So online, when you're going your online calculator, it'll have fields, right? And in one, you'll just have to type in 177, 147, and the next one you'll type in 11. And then I think you might have to press calculate and you'll see the answer. So you'll get 177, 147 mod 11. 177,147 mod 11, it will give you the answer. So I want you all to work it out, right? Work it out and you all will give me what is the result you get for each number, right? So go ahead and work it out.
Recording stopped.
Okay, so yeah, in the 3 to the n column, right? In the 3 to the n column, what did we get?
Recording in progress.
For 1, in the 3 to the n column.
3 to the n. 3.
What? 3?
Sorry, and 3 to the n column, right? 3 to the n column, yeah, 3.
Right, and then the next
9,
go ahead.
27,
Yeah,
81,
right.
43,
43,
729, 243,
243,
729, 21, 87, 65, 61, 19,683, and 59,049.
9,049.
Yes.
Right, and in 3 to the n mod 11, what do we get? The last column now, what do you get?
3,
3,
9, 5, 4, 1, 3, 9, 5, 4, 1,
all right, so,
which means it's not a primitive root of 11.
right. Did anybody else get that same answer in the last column?
I did.
Right, that same answer, right, for the last column, right? So, the 3, so, 3 is not a primitive root of 11. Good? That was just a little practice exercise there. So now let us go back to the slide. So we know when we talk about a primitive root, we know what it is about now. Good? So they say alpha. So both Alice and Bob, they share a prime alpha, primes Q and alpha, right? Where alpha is less than Q, but alpha is a primitive root of Q, right? So then in the next line, what Alice does, she generates a private key, x to the a, xa, such that xa is less than q. And Bob does the same thing for his side. He generates a private key, xb, Bob's private key, such that xb is less than q. Then what do? Alice calculates a public key, ya, which is equal to alpha to the xa mod q. And she sends it to Bob. Bob also calculates a public key, which is YB, which is equal to A to the XB mod Q, and he sends it to Alice. Good? And then Alice calculates the shared secret key, and Bob calculates the shared secret key. And they're supposed to, to get the same answer. Good?
Yes.
Good. So if you are getting problems if you are given problems on this at any time, they usually give you this information, right? So they usually give you the information here so that you could pull out the necessary stuff and do your calculation. So it becomes rather simple. Okay? So if I were to escape this, if I were to get a snip, if I were to get a snip of that, to put it on the blackboard, If you remember it, I'm just looking for how you call it, an example for you all to do, right? Okay, so first of all, this question right? So, right? So part of this problem is to show that 2 is a primitive root of 13, but we wouldn't do that, right? So what we want to find here, you are given the prime P equal to 13, right? And alpha, so therefore, in terms of the diagram, what is equal to 13? What will be equal to 13? What is the first line under Alice in the diagram? Under Alice, what is the first box? What does the first box say under Alice? Yeah, I didn't hear what you say. The first box under Alice. What does it tell us?
It
Alice
says
and
that Alice and Bob share prime Q and A, such that A is less than Q and A is a primitive root of Q.
right. So now in this problem we have here, what will be Q and what will be, well, alpha? In the problem that I
Q,
write.
Q would be well, P 13.
Right. So Q,
Alpha
so
would be
we have Q equal to 13, right? And we have alpha equal to,
2.
right, alpha equal to 2, right? Good. So I'll give you all a start there. So just keep looking down. Then they say, so Alice generates a private key. Well, a private is the same as secret, right? Secret, right? Good. Private and secret, right? So Alice generates a private key XA or a secret key XA, right? So based on what we have there, find the shared key for me. See if you could find the shared key from that. Find if it, well, first of all, find if it is possible to get the shared key. Yeah, man, it is possible. So just write down all the terms like I have written it down there. Good. All right, so I'll just put secret here is the same as private. Right? The word secret here is the same as private. Good? So you all see where I'm going with this?
Yes.
All right, so you could find the terms and work it out. You'll find out, right? So you know what is Alice generates a private key, which is the same as secret key here, right? So you all could just substitute. I mean, it might seem a little strange as you're doing it the first time, but is the question, this question is just like to work your faculties at a certain level. That's all. That's all it's about. And you're including modular arithmetic. Good. That is why we did modular arithmetic. When we do RSC, right? When we do RSC, then you will see Reverse Shamon and what is Adamir, then you will see why we did Euler's torsion function, psi n, and so on, right?
So
Uh-huh.
that given the prime, that's supposed to be Q or P?
Well, look, up here, that's now, let me underline. So Alice and Bob share a prime Q and alpha, right? Those are two primes, Q and alpha, such that alpha is less than Q, right? So a prime Q. So in this case, the prime Q is equal to 13. And look, I wrote it down here.
Right. So yeah, what I was saying was, isn't that a P, not a Q, that you have for the prime P of what you wrote, the first line?
Right, given that the prime P, so the prime is Q. A prime P is 13, which means that Q is 13. It's a prime.
Okay. Thank
Look,
you, sir.
look here, prime Q. You see where I'm underlining it? Prime Q. You see it? So prime could be P. If you put P for prime or Q for prime, it will be the same thing. Good?
Yes, sir.
Right, so
Thank
go
you.
ahead. All right, anybody made some headway as yet?
So I got the shared key to be 2.
All right, so we have Q. So what are the other terms we have? We have Q equal to 13, alpha equal to 2. What else we could find out from the information that was given the problem that I gave? Tell me, if you get the answer, you should be able to tell me this.
YA and YB?
No, from the, so the private or secret key of Bob, so and the private or secret key of Alice is 5. Good? Good?
Right. Yeah.
So what is the term
The
for that
public
private?
key.
No, look at it. Alice generates a private key. You see this across here? Let me put it in red. Alice generates a private key. Look across here. Good?
Yeah.
A private key XA, right? So look I have here. So that is XA. XA in this case, Alice is private. That is why I write private across above secret. Private key of Alice is 5. So XA is equal to 5. You see that?
Yes, sir.
And what else could we get there?
Well, XB would be 7.
Right. Did you have that?
Yeah.
XB equal to
Well, I didn't
7.
write that down because I just
Uh-huh.
knew
You
it
just
from the
substituted.
questioner.
Or you just substituted, right? So
Yeah.
the thing is to write down all the terms, right? And we want to find the shared secret key. So which one of if it's a shared secret key, it means anyone you work out should give you the same thing. And what you work out here, this is the shared secret key here of Alice. And this here is the shared secret key of Bob. That's the same key that they share. So any one of those formulas you use, you should be able to get the same answer, right? Good.
Yes, sir.
So if we use the shared secret key, let us use across by Alice. So for Alice, the shared secret key, she will use this here because Alice calculates shared secret key K. And that for her is YB, right, to the power of XA mod Q, right? So what is YB?
11.
I know, but what's the formula used for it?
Oh, alpha to the power of XB.
Right. You're going correct. So YB is equal to alpha to the power of XB mod
Q.
Q, right?
Yeah.
Mod Q. So look, they have it here. So we went down here. We went down here. We're using this formula here. The secret key K is equal to YB to the XA mod Q. And I put it up here. YB is equal to the XA mod Q, right? So YB, right? So we don't know what is YB, so we have to find it out. YB is equal to, when I come down here now, we write it out, YB from the formula, look at here, YB. They're telling you how to find YB. YB is equal to alpha to the XB mod Q. So it's equal to alpha. What is alpha again? Alpha is 2 to the XB, right? XB, look, XB is here. XB's Bob's secret key is 2 to the 7 mod Q. Q is how much again? Q is 13, right? Good. So 2 to the 7 is how much? 128?
Yeah.
Is 128 mod 13. What is the remainder when we work that
11.
out?
Yeah, I
11,
got 11 as well.
right? Which is equal to 11. So YB is equal to 11. So we could substitute across here now. So for YB, we put is 11 to the power of XA. Remember, XA is Alice's private key or secret key, which we have here, which was given the problem. So it's 11 to the power of 5 mod Q. And Q is 7. Good? And when we work that out,
Also, Q is 13.
oh yeah, sorry. 7 is
YB
Bob.
is,
Yeah.
yeah,
7
XB
is
is 7.
7 is Bob's secret key, right? So mod 13. All right. Good? 11 to the power of 5 is what? You able to get that? Was your calculator able to give you 11 to the power of 5?
Yeah. 161,051.
Right, yes, that's it. 161,051 mod 13. And we could work out that easily. Good? What we got? 13 ones are 13 and 3. 13 twos are 26 and 5. 13 threes are 39 and 11. 13 into 115 is how much? 8. Right? 8 and remainder how much? 91 and 13 is 104. And 11 and 13 into 111 is how much? Or am I going right here? 13 ones are 13 and 3. 13 twos are 26 and 5. Oh, no, it's not 13. 13 fours, 4 threes. No, 13 threes are 39, yes. 13 threes are 39 and 11. So 13 into 111 is what? It's 104. It's 8, right? And remainder what? What did you all get as the answer?
So I now see an error I make here.
So I guess 7.
7.
Right? So it's 104 and how much make 111? 104. I have 111 up here. And 13 by 8 is 104. So 4 and 7. Right? So 7 when we calculate it across here for Alice. Right? So calculate it for Bob now and see what you get. So what you have to do now, what we're going to do now, we're going to write it in what color? I'm going to write it in.
Sir, I know people go, but I'm feeling lost.
You're feeling lost?
Yeah, I'm feeling lost because this writing thing, and to me, is like a confused. I don't know where you're writing. I don't know where you're going from A to part B after you find YB to be 11, and after you do the 11
All
to
right.
power 5 mod 13, you lose me.
All right, good. So, right. So from the problem, I know what I'll do. So from the problem, we have these terms down here. We know that Q is equal to 13. We know that alpha is equal to 2, right? So this is the prime here. Prime P or Q is equal to 13, and we have alpha is equal to 2, right? Get that here. And then now, the secret key or private key of Alice is 5, right? And when we go across to the writing across here, we see the secret key or the private key of Alice. This is XA. So that is why now we put XA here. XA is equal to 5, right? You get that so far?
Yeah.
Right? And the private key of Bob is 7. So the private key of Bob, they denote it as XB. XB, right? Which is across here. So XB is the private key of Bob. So from our problem, XB is 7. Private key of Bob, right? So right, so I'm going to write those things over on top here. We have Q is equal to 13. Alpha is equal to 2. XA, this private key is equal to 5. And XB Bob's private key is equal to 7. Good? So now I could clear below here, right? Right? So now, good. So now what we want to do, is to find the shared secret key, right? This is a shared secret key. Bob should have the same thing across here. When he calculates this across here, that's the shared secret key. That's the calculation for it there. And this is also the calculation for it here, right? So let us go with this one here, right? You see where I put in the arrow? Do you see that?
Yeah.
Right? So the secret key there, K, secret key K are coming up here now is equal to YB to the power of XA, right? Mod Q. So YB. If we go across here, we will see YB. Look, YB is being calculated here. This is how we calculate YB, right? You see that? You see where I put that circle? They say YB is equal to alpha to the XB mod Q, right? So alpha is what? On top, we know that alpha is 2. 2 to the power of XB. Is it XB? Yes, alpha to the power of XB. So what is XB? We know XB 7. Look, we have that term up here. Bob's private key, 2 to the power of 7 mod Q. Q is 13 mod 13, right? And we get 2 to the power of 7 mod 13. What will it get at us? That 2 to the power of 7 is 128 mod 13, right? What answer will you get for that? Was it 11 or 12?
11.
11, right? So now we know that YB is equal to 11. Good? So then we could substitute that into here. YB for the secret key K is YB to the XA mod Q, right? This box here. So is YB, so K is equal to YB to the XA mod Q. So K now is equal to YB, which we found here. This is YB 11. 11 to the power of XA. XA is Alice's private key on top, right? We had already determined that from the problem. So it's 11 to the power of 5 mod Q. Mod Q, which is 13. Good? And 11 to the power of 5, what did I get at us again, boy? 161,051, right? 11 to the power of 5 is 160,000. 161, sorry. 161,051 mod 13, right? So modulo is the remainder. So the remainder, when we work out that, is 11, right? So that is the
How come I get 7 on my calculator? Brother?
I also got 7 as a remainder.
Oh yes, it was 7. Sorry, not 11, because I remember I had 13 by 8 was 104, and I had 111. So it's 104 and 7. Yes, that's it. So it was 7. You all remember when I was working it out, I had that? Anybody remember that? When I was working it out? Right? So it is 7. Good. So which means which means that is the shared secret key, which means that if we go across, we worked it out from Alice's point of view, right? We'd say YB to the XA from Alice's point of view. Now, if we go across, and we work it out from across here now, where I'm putting this arrow, right? So, we should get the same, we are supposed to get the same thing, because it's a shared secret key. So, if we use K is equal to, we're coming across here now, by on the bob, we say K is equal to YA to the power of XB mod Q, right? Which is equal to YA. What is? We don't know YA, right? So it's YA to the power of XB. XB is 7, right? Mod Q. Q, which is 13. So now what we have to find out is what is YA. And if we go across here, where do I find it? Oh, across here in this box here, right? YA. Bob receives YA? No. YA is up here. Look, she's calculating it here. Look, this giving us the formula up here. YA, where I'm circling, you seeing that? YA is equal to alpha to the XA mod Q. So, YA is equal to alpha to the XA mod Q, right? So YA is equal to alpha, which is 2 to the XA, which is Alice's secret key, to the XA, which is 5, mod Q is 13. So 2 to the power of 5 is equal to what? 32? 32 mod 13. The remainder is equal to what? 26 and how much? 6? Am I correct there, people? Right? We get 6. Right? So we know that YA is equal to 6. Right? So now we could calculate the key from across here. Right? We get YA. So I'll write it again. K is equal to YA to the power of XB, YA to the power of XB, right? Mod Q, which is equal to, so YA is 6, mod Q, mod 13, right? So 13 into 6 is 0, being the 7. Good? If we use the formula, A is equal to Q by N plus R. So A is 6, right? 6 is equal to what? N in this case is what? What is N? N is 13. No, Q by N. That's now. What are we finding? 6 mod 13. Good? 6 mod 13. And if we're using the formula, A, so A will be the unknown. Good? A is the unknown. So we say A is equal to Q by N, right? Q by N plus R. So what is Q in this case? And
13.
what is N? So A is the unknown, right? So A is equal to Q by N plus R. Okay, so if we don't do it that way, how do we do it? We say 13 into 6 is what?
I have a question. I thought you're supposed to do, since the formula is y to the power xb, I thought you're supposed to put 6 to the power 7.
That's not what it is. YA, yeah, something is wrong there. YA is equal to what? YA is equal to alpha to the XA mod Q, right? No, sorry. My mistake. K is equal to YA to the XB mod Q. K is equal to YA. So what is YA?
Right, so y is 6 and xb is 7.
Right, we had worked out YA here, yes. So I made a mistake. Right, so at least one person is awake. Right? So YA is how much you said when we work it out across here?
You get 279,936 more 13.
Right, so let me put this up here. So look here, we get YA is equal to 6, right? So it will be YA, which is 6 to the power of XB, right? XB is what? Look, XB.
xb is 7.
Right. Mod Q, and Q is 13, right? And 6 to the power of 7 is what?
That is 279,936.
All right, so that is 6 x to the y 7, 279,936, right? Is equal to 279,936 mod 13. And the remainder you get when you work that out is what?
I guess 7.
Right? You get 7. Okay? So in that case, we see when we had worked it out across here, at first, we had gotten 7 here, and then we come and we get 7 here, right? The shared key, right? If it's a shared key, it's the same thing both of them will have. Okay? Everybody clear on that? It's just a matter of
Yes, sir.
substituting into what is given. If you are getting a problem on this, you're usually given the diagram, right? The same diagram I have here with Alice and Bob, and you just substitute in,
At scale.
right? So you'll just substitute into it. Good. So so with respect, all right, let me just.
Recording stopped.
Right. So with respect to the lab, some people say I didn't open it back as yet. Okay, so what I want you all to do is to give up whatsoever you have. We can't continue going on it forever. Right. So I will leave it. I'll open it for until tomorrow night. If it isn't open, right, I'll open it back so that I'll have until tomorrow night to upload it. Okay, and just give up what you have. Right, folks?
So what is that, the lab?
Yeah. I saw some
Oh,
people
okay.
some people send me some emails saying that they didn't see it open. So if I didn't open it, right, I was supposed to open it, I knew. if in case I didn't open it, I will reopen it, right? So, in fact, I'm going to do that now because I just want to do something else totally different, and then end the class. So, let me share this. Share. So I can share this. All right, so if I go to here, here, right? So it was until the 28th, so I'll open it back. So I'll edit. What is the date tomorrow? Today is the 3rd, so tomorrow is the 4th.
Third.
Tomorrow is
Before?
tomorrow is the 4th.
Yeah.
Right? Right. So I want you all to help me with this. I want you all, everybody, to look up let us see the greatest or the biggest data breaches or cyber security breaches in 2025. Just type in that and see what you come up with. And we'll discuss and we'll see which one we will go to. I want to show you all something. Just type in that and you all will tell me what you get.
So what we typing?
Couple.
Biggest cybersecurity breaches or biggest data breaches in 2025.
With regards to cybersecurity.
So, can you just say it again, sorry? I was breaking up a little bit a second.
Okay. The
On my
biggest data breaches or the biggest cybersecurity breaches of 2025. Right? And see what you come up with there.
Excuse me, sir.
you want a list?
No.
Are
You
you
don't tell me. I just want to hear what different people get, and then we'll choose one. That's so much.
excuse me, sir. Are you limiting it to data breaches in Trinidad or worldwide?
No, it will be worldwide because I say just type in, so it will be worldwide.
Yes, a couple showed up.
A 4 billion record breach in China.
All right, 4 billion record breach in China. Okay, anybody else has anything that is big?
SK Telecom SIM authentication data breach.
All right, they didn't say how many people it affected.
Roughly 26.96 million customers.
Million.
Yeah.
Right, and the one from China was billion. Right, anybody else? Anybody else? All right, so
So
There's
anybody
another
talk
one
about
with
the go ahead, Gideon.
there's another one with Yale New Haven health data breach, roughly 5.5 million people.
million.
Million.
Okay. The person with the 26 million. All right. With the 26 million, what was it? What data breach that was? The 26 million?
26 million. I think that was me.
Somebody.
Yeah, that was me. The SK Telecom SIM authentication data breach.
SK
Telecom,
SK Telecom,
SIM authentication.
SIM
Yeah,
authentication.
data breach.
Right. So I just want to see. Right. So um, so I'll just read it, okay, folks? Right? So are you all seeing my screen? I wonder if I'm sharing the screen more.
Yes,
Sharing
it's being shared.
Right, good. So I'll just read it, right? So in April 2025, SK Telecom, that is South Korea, largest mobile carrier, formally notified regulators of a significant data breach that compromised sensitive SIM card data belonging to nearly 27 million users, right? Following an investigation, the Ministry of Science and ICT and the Korea Internet and Security Agency, KISA, concluded in July 2025 that SK Telecom was negligent in its account information management practices and in complying with its breach reporting obligations. As a result, the company was fined 30 million won. That is approximately 22,000 US dollars, right? So what happened? An unauthorized third party infiltrated SK Telecom systems and deployed a sophisticated malware strain of BPF DOR. This backdoor tool exploits the Berkeley packet filter feature in Linux system, allowing attackers to bypass traditional security mechanisms. The malware was discovered on at least 28 servers with 33 distinct variants identified. The breach is believed to be in the work of an advanced persistent threat group, potentially linked to Chinese or North Korean, right? Actors or hackers or how you want to call them, although definitive attribution has not been established. So they can't really pinpoint who did it. So what was stolen? The attackers access and exfiltrated, that is downloaded and whatsoever, downloaded subscriber identity module data, right? So subscriber identity module data. So that is the data that that is associated with, let us say, probably different phone numbers and so on. So subscriber phone numbers, international mobile subscriber identity numbers, authentication keys, management data used in SIM processing. Good. While SK Telecom initially asserted that no personally identifiable information such as birth of dates or payment data had been compromised, subsequent reports confirmed that some names and birth dates were indeed accessed. As of the date of publication, there is no confirmed evidence of misuse of the stolen data. Right? So, right. So what I want to know, right, from this, right? How does this impact the security triangle? Good. So everybody could bring it up on their screen. Could bring up this SK Telecom breach on its screen on the screen. Right? So how does this impact the security triangle?
Well, it affects confidentiality because the confidential information is now exposed and no longer confidential.
Right? And then what you have to do is to take out, you see, elsewhere on the internet, you'll get the same thing, but they might put in more information. So now what you said there is very good. But what you have to do now is to identify something in what is given to show that the confidentiality so was actually, you know what I mean? Give something to back up that what you said then. Right? From the narrative we have here. All right, so everybody's supposed to have it up. So if I move away from this page, so I just going to the next page that dealt with it to see if they give me more information. Right, so when you look at it, what in it actually expose? So you have to look at it and tell me, right, how does it affect the CIA triangle, right? Confidentiality, right? It exposes people's personal data. And what is an example of that exposure in the narrative that is given?
Wait, so did you just ask a question?
Huh?
Did you just ask a question?
Yeah, I say I want somebody told me that the question I asked was how does it affect the CIA triangle? Okay? The security triangle of
Right.
confidentiality, integrity, and availability. And one person said that
It affects confidentiality.
right, the confidentiality, right? Of maybe users of that telecom company and so on. But point out an example in the narrative given there, in the reading, point to give me an example of where that confidentiality was, where it was breached. So you're supposed to have it up. It is right there. Somebody could actually tell me something, right? Showing how the confidentiality was breached.
They exfiltrated the USM data.
User data, all right. And here I'm saying the compromised servers also stored unencrypted personal details, right? Including names, birth dates, email addresses, phone numbers, right? Good. You see that?
Yes.
Right? This is the next site I went to, right? And so usually plenty different people, plenty different security sites and so on does put up these breaches, right? So how does it affect now the integrity of data? How could it affect the integrity of data? If they did that breach, if they exfiltrated stuff, could someone have gone in? Could they have gone in and changed up some of the things inside the database? Huh? Is that possible? Since they had access to the database. Good,
Well, yes.
right? So in integrity and what, and you also have to look inside there and see if you can find something that ties in with the integrity. Right? So here I'm watching they say that while logs for December the 3rd, 2023 to April 24th, 2024 confirm no IMEI data was leaked, the period from June 15, 2022 to 2nd of December 2023 lacks data logs entirely. Good? So something strange about there. It lacks data logs, right?
Yeah.
Okay, so how could that affect the availability now? Availability, how does this bridge tie into availability?
Well, considering that they would have caused security issues with SIM company,
Uh-huh.
the users of those same SIMs, which they would have with different services or whatever they like, they wouldn't have access to any of those anymore. So the availability of information that you get with regard to the SIM data is just no longer accessible due to the security.
All right, yes. That could be a valid point, yes. And there is something else. Now, remember, you all remember the other the other triangle? The EEE triangle?
A triangle.
Yeah, the EEE triangle was for what?
AA.
AAA triangle, assurance, anonymity, and what? Was it authentication?
Was it?
Right, the EEE triangle. So how does it relate to that also? So you see, sometimes an exam might come and they might just give you, well, explain the CIA triangle or the EEE triangle, you know what I mean? But here now it is applied, right? So a sort of a training you all. Good? A sort of a training you all for the future. So they say they additionally discovered malware web shell was for the initial penetration purpose. So which means what they did is they loaded on some sort of a malware. Good? They additionally discovered that malware web shell. Good? So what I want you all to do during this week, right, is because I want to bring up one of this next week again also. I want you all to look at a data breach, right? I wouldn't put it in writing, I'll just tell you all. Go and look at a major data breach and see how it affects, how it ties in, or how it affects the elements of the CIA triangle and of the EEA triangle. Okay? And within the data breach, you must be able to pull out examples, right, to back up what you say. Okay? Folks?
So you said it
Yes,
was
sir.
the look up a major data breach.
Right?
Give examples for how it affects the CIA triad.
Right. That's the way. But first of all, before you say give examples, right? So you look up a major data breach, right? And see how it affects the elements of the CIA triangle. Good? So the elements of the CIA triangle are confidentiality, integrity, and availability, right? See how it affects the elements of the CIA triangle and give examples from the narrative or from what you read, right? to back up whatsoever you say, right? So, for instance, somebody said that the confidentiality of people's data was breached. Good. And then in the narrative here, I saw where like unencrypted details, personal details such as names, birth updates, and emails addresses. Good. Shows that the confidentiality, that is where the confidentiality was breached there, right? And the availability, or was the availability breach? Well, as somebody said that since those SIM cards, right, which are tied to a service, since those SIM cards were breached, the people, it is possible that the people could not have had access to certain services. Okay? And then you look at integrity, right? So I want you all to look up a major breach, data breach, because next week I'll be doing something similar, and I'm going to expand the I'm going to expand the amount of questions, okay? Because like in your exam, you'll be getting a question like this, and it's worth 20 marks. So it is something that you really don't teach, right? Well, you teach that, or you go through the notes, which you all have already gone through, on confidentiality, integrity, availability, CIA triangle, and the assurance, the AAA triangle of what was it? Authentication, anonymity, and assurance. Good, right? So you went through that, but now you have to know how to apply it to show how it relates to data breaches, right? And that to prevent the data breach, right? To prevent breach of confidentiality, to prevent breach of integrity, to prevent availability, we're also supposed to be able to say like what should have been done, what proactively should have been done. Good, folks.
Understood.
It is like an applied question. Good.
Yes, sir.
So, and we could only handle it through like discussion, right? So that 4 billion, the Chinese data breach, that was a good one, right? That was a good one. But you all could look up any one of them. You had the Adaha, right? You had one with um a couple billions in India. I think that was the Adaha. Yeah, it has a lot, right? You just have to look it up and see how it affects or it relates to the CIA triangle negatively or positively. Well, most likely not positively, but negatively. How it relates to the CIA triangle and how it relates to the EAA triangle also. Okay, folks? Right? And um, don't forget to do that problem 2 to the power of 1,115, right? Do that problem and so next week. Good? Because I want you to get accustomed to the modular arithmetic because you see you have the modular arithmetic in the key exchange, in the Diffie-Hellman key exchange. Well, in fact, we didn't even go through we didn't even go through the how you call it, well, the notes, right? But the notes are embodied in that diagram, what the Diffie-Hellman key exchange is about, right? So Alice and Bob, they share two primes, right? P and Q, right? Not P and Q, sorry. Q and alpha, or P and alpha, Q is the prime or P is the prime, but let us leave it as Q and alpha, right? Where alpha is a primitive root of Q, right? So both of them have that. And then Alice now, what does she do? she calculates a public key. And I think she sends it to Bob, and Bob calculates his public key and he sends it to Alice. Good? And from there, they could compute the sorry, each of them computed what? Their private key at first, and their secret private key. Did they do that at first? That's all. Let me go to the PowerPoint and let me share it with you all. It's shared. Right, let me make it full screen. All right. So Alice generates, she generates a private key, right? And Bob generates a private key. Good? Then Alice calculates a public key and Bob calculates a public key also, right? And they receive each other's, they exchange their public keys. Good? And from that, you could get the secret key. Right? So we wouldn't be doing elliptic curves and so on. What I want to go on to, but not tonight, is the RSA algorithm, where in that I think you use Euler's torsion function. I think you use that in the RSA algorithm, right? And when we are doing the RSA algorithm, we'll go back now to the Euclidean algorithm and do the extended Euclidean algorithm. Remember, we did the Euclidean algorithm where, if I could share again, we did the Euclidean algorithm where we had like two large numbers like 24, 240, 261, right? And another number 16, 762, right? And we did the Euclidean algorithm where we had the quotient here, we had the dividend here. The dividend is a larger number. We had the divisor here, smaller number, right? Smaller number, and then here what we had? We had the remainder here, right? So for instance, like if they tell you to find the GCD of, let us say 788, well, let me take something of 144 and let us say 24. Good? So the larger number will come here, 144, and 24 will come here. And oh no. This would work. Because not 144 and 24, right? That's not one. 44 divided by 272. Okay. I want to put another number. 48. All right. So let us say we wanted to find, right, for 48, right? Right, the GCD of 144 and 48. Good. So we put the quotient across here. So what will go across here? 48 into 144 will go how much time? Oh, no, it still would work because we'll get 48 by 3. It's somewhat 3 is 24. 4 is 12 and 2 14. Still didn't choose a good number. So if I choose, let me see. Let me just arbitrarily choose, let us say, if I choose 32. Right? 32 into 144 is how much? 32 by 2 is 68. 32 by
4.5.
no, not 4.5. So it's 32 by 4 will give us how much? 128, right?
28.
So the answer, the quotient will be 4, and the remainder will be 128, and how much to make 144? That will be what, 16? Right?
Yeah.
Right. So, and then what we did is that we did a shift. This 32 will come here now, and then the 16 will come here. Eh? And we say 16 into 32 is 2, and the remainder is 0. Right? So then we shift. The 16 will come here in this, and the 0 will come across here in this column. And we know when we have 0 in this column, so this column here was A column, this was, you could call this B. When we have 0 in this column, we know that, well, the number we get before, which would be 16, will be the GCD. Good?
Yes, sir.
Right? So that was Euclid's algorithm, but then there's something called Euclid's extended algorithm, which we might take a look at next week. And it all has to do with modular arithmetic. All of this has to do with modular arithmetic. Right? With Euclid's extended algorithm, we actually use that in what you call in the RSA algorithm. So we'll probably look at that next week. Okay, but I just want you all to do that. That's a little problem in Fermat's theorem. I want you all to do that. And remember, I want you all to look at a data breach. Good? And see how you could relate it to the CIA triangle and how you could relate it to the AAA triangle. Okay, folks? So we will look at another one next week in more detail. Right? So
Yes, sir.
that will be it for tonight. So if there are no questions, I would like to sign out.
So you're taking a roll already?
Yeah.
Oh, no, I didn't take the role. Very good. That's a good question. So I'll have to share again. I want to share. Okay, maybe share this. Is it this? No. Right, this now. Take this down. Take this down. Bring this up. Share. Then we have to go to what attendance. Okay, Nafisa, are you here?
Present, sir.
Ida Bramble,
Present.
Zion Karut, Nilan Kasim,
Present, sir.
Shay Castillo, Gabriel Charles.
So Zion is present.
All right, Zion, right. Gabriel Charles, Liam. Okay,
Yeah, say present in chat, sir.
right. Ethan Clark. And what about Shay Castillo? Ethan Clark. Okay, Chris Dukaran. Miss Gandial.
So Chris was present, but it looked like his internet dropped.
All right, Chris was Chris. Okay. All right, so somebody knew Chris. What about Ethan? I thought I saw Ethan Clark. All right. Miss Gandial, Josiah, Ruben,
Yes, sir.
right, Shivana Jawahir, right, Zachary Joseph.
Yes,
So
sir.
Shivanan was also here.
All right, good. Zachary,
Yes, sir, I'm here.
Majid Khan,
Present, sir.
right. When I was in school in college, there's a guy named Majid Khan also. So I don't know if you're a time traveler or what. So Aaron Lewis,
Yes, sir.
Michael Martin,
Present, sir.
Gideon Matthews,
Present.
Darius Naranjit,
Present, sir.
Mohini Odet,
Present, sir.
Miguel Pascal,
Yes, sir.
Azariah Rahman,
Present.
Jonathan Rajkumar, Shivanan Rampasad,
Present, sir.
Gabriel Samaru,